Hello guys, welcome to our channel. So today we are going to continue with our massive A-level revisions, and today we are having this question paper. This is June 2023 session, physics paper 3 for A-level. So this is Zimsec. Okay, so it doesn't matter that you're not doing Zimsec. Physics, just physics. When you're talking about Kirchhoff's laws, when you're talking about the principle of conservation of energy, the Ohm's law, these are still the same concept, both for Zimsec and Cambridge. Okay, so if you're doing Zimsec, just pay attention to this instruction to the candidates. So in this question paper, this is paper 3, guys. We are required to answer 4 questions. In question number 1, it is compulsory. So this question number 1 is compulsory, and today we are going to put more of our focus on this question number 1. This is of question of classic mechanics and general physics. Okay, so let us dive into a question paper. So the question number 1 says, state the effect of random and systematic errors on measured values. So what we need to do here is to start by explaining what is meant by this term random, and also what is meant by this term systematic error. So what is random error and what is systematic error? Random error, it is when measurements are scattered about the mean value. So it is when measurements are scattered about the mean value. So this is the definition of random error. And then for systematic error, it is when measurements are fault in one direction by a constant error margin. Okay, so this is the definition of systematic error. It is when measurements are fault in one direction by a constant error margin. So an example for systematic error, we have zero error. So zero error, it is an example of systematic error. And also what you need to know about systematic error is also that it is a constant error margin. It has a constant error margin. So just highlight here that it has a constant error margin. That is fault in one direction. So when you are saying in a fault, it is a fault in one direction. Let's say we are using an instrument that or a stopwatch. Okay, we can use a stopwatch that is 1 second ahead. So our measurements will always 1 second greater than the actual value. So that is what we call the systematic error. So we have measurements that are fault in one direction, and they have a constant error margin. Okay, and then for systematic error, a good example for systematic error, we have parallax. Error. So a good example of random error, it is a parallax error. So random errors, it is when measurements are scattered about the mean value. So parallax error, it is a good example of what we call random error. But the question requires us to state the effects of random and systematic error on measurements. So what we need to understand, it is what is random error and what is systematic errors, okay, and their effects on the measured values. Okay, so what you can do here is to say for random error, there's a scattering of measurements about the mean value. That is the effect of random error. And then for systematic error, the effect of systematic errors on the measured values, it is that there will be a deviation of measurements with a constant error margin in one direction. That is the fault. It is when measurements are fault in one direction with a constant error margin. So these are the effects of random error and systematic errors. You also need to understand what is meant by these two terms, precision and accuracy. So we have these two terms. Other two terms, we have precision and what we call accuracy. Okay, so precision, it is the measure of deviation of measurements from the mean value, and then the accuracy, it is the measure of deviation of measurements from the true value. So the major difference between precision and accuracy, it is that for precision, it is the measure of deviation of measurements from what? From the mean value. So for precision, we are interested with the mean value or the average value. And then so you also need to understand that this term here, mean, simply means average. So mean is the same word as average. So precision, it is the measure of deviation of measurements from the mean or the average value. And then for accuracy, it is the measure of deviation of the measurements from the true value. Okay, so we're not talking about accuracy. We are interested with the true. We are interested with the true or the actual value. So it's either the true or the actual value. So what you also need to understand under this topic of randoms, errors, systematic errors, precision and accuracy, it is that when random errors are higher, this reduces precision. When random errors are higher, this reduces precision. Why? Because from our definition of precision, it is the measure of deviation of measurements from the mean value. And then random error, it is when measurements are scattered about the mean value. So the scattering of measurements about the mean value, if we increase that scattering of measurements about the mean value, it reduces the precision of measurements, the deviation of measurements to the mean value. Okay, and also you need to understand that the increase in systematic error reduces accuracy. Okay, so from our definition of systematic error, we say systematic error, it is when measurements are fault in one direction with a constant error margin. So if we increase the fault of measurements in one direction by a constant error margin, we also reduces the accuracy of those measurements. So the higher the, let's say it's random errors, so if we increase random errors, we are decreasing what? Precision. Okay, and also if we increase systematic error, we are also decreasing what? Accuracy. We are decreasing accuracy. So these are the most important information under this topic of general physics: random errors, systematic errors, accuracy and precision. The increase in random error reduces precision, the increase in systematic error reduces accuracy. Okay, and let us move on to the next part of our question, which says in an experiment to determine the density of a spherical ball, a student measured and recorded the following readings. So we have the mass of 0.6 grams plus or minus 1%, and we also have the diameter D. So the diameter D is equal to 2.14 millimeters plus or minus 3%. So we are required to describe how the accuracy in the measurement of the diameter can be achieved. So with this term, accuracy, the measure of deviation of the measurement from the true value or the actual value. So how best can we increase the accuracy of the measurement? So for us to increase the accuracy of the measurement, we try by all means to reduce systematic errors. Okay, so if we want to increase the accuracy of the measurements, we reduce systematic errors, and if we want to increase the precision of the measurements, we reduces or we decreases the random errors. So here we are talking about the reduction in systematic error. So how best can we reduce systematic error? So the causes of systematic error: number one, we have fault instrument. Okay, so for us to increase accuracy, we can use instrument without fault. Okay, because this is the fault, this is the cause of systematic error. So for us to correct this error, we reduces the fault in our instruments. So that is the one way of increasing accuracy on a measurement. Okay, so we can talk of fault instrument, we can talk of adding. So this is another way of correcting systematic error. It's either we add or subtract the error margin. So it's either we add or we subtract the error margin. So if we add, let's say the error margin was plus second. So for us to have to increase the accuracy of the measurement, we subtract the error margin because our stopwatch, it is 1 second ahead. And for us to correct the systematic error when our measurements are 1 second behind, we add that 1 second. So this is another way of increasing the accuracy of our measurement. So if we have managed to correct these 2 points here, the fault in instrument, if we manage to reduce the fault on our instrument or to add or subtract the error margin, we have managed to increase the accuracy in the measurement of the diameter. Okay, and so let us move on to the next part of our question, which requires us to determine the density of the ball and its uncertainty. So we're required to determine the density of the ball and its uncertainty. So the first thing, or the first stage, it is to have the formula of density, because we're required to calculate the density. So density is equal to mass over volume. So this is the formula for density. So density is equal to mass over volume, but the volume of a sphere, it is equal to 4 over 3 pi r cubed. So in this case we have diameter, so we need to have a relationship between radius and the diameter. So twice of radius, it is equal to diameter, therefore radius is equal to diameter divided by 2. So you can substitute d over 2 for r to say volume, it is equal to 4 over 3 pi d over 2 cubed. Okay, so it is now 4 over 3 pi, and our diameter, it is d cubed, and 2 cubed, it is equal to 8. Okay, so this gives us 4 over 3 multiplied by 1 over 8. So if we multiply 4 over 3 by 1 over 8, this 4 into 4 is 1, 4 into 8 is 2. So this gives us pi d cubed over 6. So this is our volume. Therefore, the density, it is equal to 0.06, the mass of the ball, divided by pi d cubed multiplied by 6. Okay, because we are dividing a fraction. So density, it is equal to 0.06 times 6 divided by pi times what is our diameter, is 2.15 cubed. Okay, so density, it is equal to 0.06 times 6 divided by pi times 2.15 raised to the power 3. Okay, so this gives us 0.0115 grams per cubic millimeter. Okay, so this is our density, and let us calculate the uncertainty of the density. So here we are having percentage uncertainties both for mass and diameter. So the percentage uncertainty, it is fractional uncertainty multiplied by 100. Okay, so the uncertainty in density over density multiplied by 100, it is equal to the uncertainty in mass over mass multiplied by 100 plus the uncertainty in diameter. But here that our diameter is raised to the power 3, so it is 3 times the uncertainty in diameter divided by diameter times 100. Okay, like this. Therefore, the uncertainty in diameter, in density divided by density by 100, it is equal to the percentage uncertainty in mass. It is equal to what? It is 1 plus 3 times the percentage uncertainty in diameter. It is 9, because we are multiplying 3 by 3, and this gives us 9. Therefore, the uncertainty in diameter over diameter times 100, it is equal to 10, and we can divide both sides by 100 to say the fractional uncertainty in diameter, it is now equal to 0.1. So let us multiply both sides by the diameter, by the density, to say the uncertainty in density, it is equal to 0.1 multiplied by the density, which is equal to 0.0115. Okay, so the uncertainty in density, it is now 0.1 multiplied by 0.0115. So our answer, it is 0.00115. Therefore, the uncertainty in density, it is equal to what? 0.001. So this is the uncertainty in density, and the density with its uncertainty, it is now 0.012 plus or minus 0.001, and our units, grams per cubic millimeters. So here is our density with its uncertainty. Okay, and let us move on to the next part of our question. So the next question is here, it's part B. So the next question says, identify vector and scalar quantities from the following quantities. Okay, so this is a straightforward question. So what you need to know, it is what are the vector quantities and what are scalar quantities. So a vector quantity, it is a quantity that has both magnitude and direction. So that is what we call a vector quantity. And then a scalar quantity is a quantity that has only magnitude, or it can be described fully using its magnitude only. And in this case, we are required to group all these quantities into two groups. There are other ones under the vector quantities and other ones under the scalar quantities. So electric charge, it is a scalar quantity. So let me use a blue color for scalar quantities. So the electric charge, it is a scalar quantity, and gravitational potential, it is a scalar quantity. Decay constant, it is a scalar quantity. So we are having 3 scalar quantities, and then vector quantities having magnetic flux density, it is a vector quantity, and also electric field strength. So these are the 2 vector quantities, and electric charge, gravitational potential, and decay constant, these are scalar quantities because they only have magnitude and not direction. And let us move on to the next part of our question. So this is item 2. So the question says an aeroplane, so let me wrap this. So the question says an aeroplane flying horizontally. So just highlight this, it is horizontal. The aeroplane is flying horizontally with a speed of 250 meters per second at a height of 4.5 kilometers, and it drops an object. Okay, so we are required to calculate for the object the time taken to reach the ground, number 1. And number 2, the horizontal distance traveled from the point it was dropped to striking the ground. and number 3, the velocity with which it strikes the ground. Okay, so here is our aeroplane. It is moving with a speed of 250 meters per second, and if it drops an object, that object will also move with a horizontal speed of 250 meters per second. But so let's say this aeroplane is dropped the object at this point, so this object will move like this. Okay, so here at this point we're having a speed of 250 meters per second. So this object, it has only 250 meters per second, the horizontal speed. So the vertical component of speed at this point, it is equal to 0 meters per second for this object, and then it starts to accelerate vertically from 0 meters per second to any speed. That's why we are being asked to calculate the velocity with which the ball or the object strikes the ground at this part of our question. So if the ball have only this horizontal speed of 250 meters per second, we shouldn't have this question. Why? Because the horizontal component of speed, it is always constant throughout the projectile motion. So let us calculate the time. So we want to calculate the time taken to reach the ground. So we are having our SUVAT. So it's SUVAT. And then S is for displacement, U is for initial speed, V. So this is V is for final speed, A is for acceleration, and T is for time. So the displacement, the vertical displacement, it is the height. So it is 4.5 kilometers, and then in meters, it is 4,500 meters. So this is our height. In the initial speed, the initial vertical speed, it is 0. And then the final speed, we don't know the final speed, and so we can leave it. And then for acceleration, it is G, the acceleration due to gravity. And because we are starting from above, G is positive, but if we were starting from below, G will be negative. So what we want to calculate is time. Okay, so we have 4 equations of motion. S is equal to ut plus half at squared, and S is equal to half u plus v times t, and v squared is equal to u squared plus 2as, and also v is equal to u plus 80. So these are 4 equations of motion. So we want to calculate time, and we want an equation without v. So an equation without v, we can eliminate this one because it is v, this one, and this one. So we're going to be left with the first equation. So the first equation, it is S is equal to ut plus half at squared. So our S, it is 4,500 being equal to our u, it is 0. So the ut term, it is equal to 0. So 4,500, it is equal to half g t squared. Okay, and let us multiply both sides by 2 to get rid of this fraction on the left hand side, on the right hand side of the equation. So it is now twice of 4,500 divided by g. It is equal to what? To t squared. Okay, so 2 multiplied by 4,500 divided by 9.81, it gives us what? It gives us 917.4 being equal to t squared. And let us apply square root both sides. Therefore t is equal to square root of 917.4, and this gives us 30.3 seconds. So this is our final answer, the time taken to reach the ground. Okay, and let us move on to the next part of our question, which says the horizontal distance traveled from the point it was dropped to striking the ground. So if I said, let's say here is our aeroplane, and it drops an object at this point. The object will move like this. Okay, move like this. So this is the point at which the object was dropped. So we are required to calculate this horizontal displacement. So given that the horizontal speed, it is always constant, we can simply use this equation. S is equal to ut. Why? Because our horizontal speed, it is always constant. So the horizontal distance, it is S being equal to what is our initial speed, it is 250 meters per second, multiplied by the time of flight, which is 30.3. So the time of flight, it is the same for both the vertical motion and the horizontal motion. So the horizontal distance moved, it is 250 multiplied by 30.3, and this gives us 7,575 meters. So here is our horizontal distance traveled from the point the object was dropped to striking the ground. And lastly, let us try to answer the last question of our item 2. So the last question says the velocity, calculate the velocity with which it strikes the ground. So given that our horizontal component of velocity, it is always constant, it is 250 meters per second. So if our object starts from this point up to this point, we have this horizontal speed, and also we have this vertical speed, and this is our resultant speed. So what we are required to calculate is the resultant speed, not the vertical speed. So this is the misconception one can do. This is a common error with most of the students, to say they calculate the vertical speed and then think that this is the required velocity, but the required velocity is the resultant velocity. So the resultant velocity, it is the resultant velocity for both the vertical component of velocity and the horizontal component of velocity. So the horizontal component, it is 250 meters per second, and then the vertical component, that is what we are required to calculate first. So let us calculate the vertical component. So use our SUVAT again. So our S, it is 4,500 meters, and our initial velocity, it is 0, and we want to calculate the final speed, and our A is equal to G, and then our time, it is what, 30.3. okay, and now we have our 4 equations of motion here. So these are the equations of motion. S is equal to ut plus half at squared, S is equal to half u plus v times t, and then v squared is equal to u squared plus 2as, and v is equal to u plus at. So we want an equation without t, because this is a calculated value, so try to avoid using of calculated values. So we want an equation without t, so obviously we are going to use the third equation, v squared is equal to u squared plus 2as. So what we want to calculate it is v squared. So v squared is equal to u squared plus 2as, and our u is equal to 0, therefore v squared is equal to 2as, and v is equal to 2 multiplied by, what is our a, it's 9.81, multiplied by our s, 4,500. okay, so it is the square root of this. So v is equal to square root of 2 multiplied by 9.81 multiplied by 4,500. okay, so v is equal to 297 meters per second. So this is our final speed, it is 297 meters per second, so it is 297 here. So for us to calculate the resultant speed, given that we have something like this, and this is our resultant, and we are having a right angle, so it's 297 here, and here is 250. So for us to calculate this resultant speed, we can use our Pythagoras theorem to say RV squared, it is equal to 297 squared plus 250 squared. okay, so RV squared, or the resultant speed, it is 297 squared plus 250 squared, and if we add this, we'll get the final speed squared being equal to 157.09, like this. So the resultant speed, it is the square root of this, so it is the square root of 150,709, and this gives us 388 meters per second. So our final speed, it is 388 meters per second. This is our velocity, and we also need to calculate this angle here. So given that we are having adjacent and opposite, you can simply use tan. So tan theta, it is equal to opposite over adjacent. Because why are we calculating direction? Velocity is a vector quantity, so we need to give the direction of that velocity, because it is a vector quantity, unlike speed is a scalar quantity. So we need to define these two terms. Velocity is a vector quantity, and the speed is a scalar quantity. So tan theta is equal to, what is our opposite? So our angle is here. Our opposite is what? 297 over what? 250. okay, so if we apply arctan both sides, to say it's tan theta being equal to arctan 297 over 250. This tan and arctan we cancel to be left with theta being equal to arctan of, so we are now having arctan of what? 297 divided by 250, and this gives us 49.9. so it's 49.9 degrees. So this is the direction, or the angle of the velocity. So our resultant velocity is 388 meters per second, acting on this direction or under this angle of 49.9 degrees. okay, and let us move on to this third part of our question, which says suggest why in practice the velocity calculated in item 2 number 3 is more than the actual velocity when striking the ground. okay, so we are required to explain why the calculated value of 388 meters per second, it is more than the actual value. So the reason why it is more than the actual value, it is that these 4 equations of motion here, they are only theoretical equations. Why am I saying these are the theoretical values, theoretical equations? the assumption we are using here, it is that we have two conditions for this equation to be applicable. The first condition, it is constant acceleration, and the second condition, it is in the motion in a straight line. But in real life or in practice, we cannot maintain a constant acceleration. At the same time, we cannot move in a straight line. So this simply means that this equation, they only apply theoretically. So the reason why the calculated value, the 388 meters per second, is more than, it is that we have neglected the effect of air resistance. So if we are to appreciate the presence of air resistance, the velocity will be less than 388. So to suggest a reason why the calculated velocity is more than the actual velocity, we can talk of the effect of air resistance. So the effect of air resistance tends to reduce the vertical component of speed, and if it reduces the vertical component of speed, the resultant speed will also decreases. So that is the reason why in practice the velocity calculated in item 2 number 3 is more than the actual velocity striking at the ground. Okay, so let us move on to the part C of our question. So the question says a block of mass 120 kg is floating in water in a pond, and the density of water is 1000 kg per cubic meter, and we are required to determine the upthrust acting on the ice. So the first thing we need to do is to define the term upthrust. So upthrust, it is equal to weight according to weight of the fluid displaced according to Archimedes principle. But what gave rise to the upthrust? So upthrust, let's say we're having a beaker like this and something like this. So as you can see, this object is well immersed in the fluid. So we have the weight. You have the weight of this block, and there is what we call upthrust. Okay, so from the definition of pressure, pressure it is equal to force over area. So pressure in fluids, it is rho GA. Okay, because we have derived this equation rho GH from this equation force over area. So pressure in fluids, it is rho GH, and this simply means that pressure increases with depth in fluids. So pressure at this point here, it is less than pressure at this point. So if pressure increases, and we use this equation, pressure is equal to force over area, and if we want to calculate force from this equation, force, it is equal to the product of pressure and area. So if pressure at this point is greater than the pressure, it is less than the pressure at this point, this simply means that force at this point, it is greater than the force at this point. So there will be a resultant force upward. Okay, so this is what we call the upthrust. Okay, so we're required to calculate the upthrust of the acting on the ice, given that the water has the density of 1000 kg per cubic meter and the mass of 120 kg. So upthrust, it is equal to rho GV. So this rho is the density of the fluid, and this is the acceleration due to gravity, and this one is the volume. Okay, so from our definition or the principle of Archimedes principle, upthrust, it is equal to the weight of the fluid displaced. So weight, it is equal to mg, and our m, mass, from density, it is equal to mass over volume. So if we multiply volume by density, our answer will be mass. Okay, so rho v, it is equal to mass. That's why we are saying upthrust is equal to rho v g, and this g, it is for the acceleration due to gravity. Okay, so our upthrust is equal to rho g v. But what you need to understand here on this question, it is that this density is we are not using this density. Why? Because we don't have the volume, but we have the mass. And you need also to take note of this term here, floating. So if the object is floating in water, this simply means that weight is equal to upthrust. So if weight is equal to upthrust, our upthrust, it will be equal to mg. So our upthrust, it is equal to 120 multiplied by 9.81. So it's 120 by 9.81, and this gives us 1077.2. So it's 1177.2 newtons. So here is our upthrust. Okay, so this was a tricky question. So it was very difficult to understand that this 1000, we are not using this 1000. Okay, alright, so let us move on to the next part of the question, which says when a block of ice in a beaker melts, there is a change. So let me rub here. So there is a change in the level of water in the beaker, and we're going to explain this observation. So what is the observation? They're saying the observation is the change in the level of water in the beaker. Okay, so this question was wrong starting from this point. This question was wrong starting from this point up to this point. why am I saying this question is wrong? They are saying when a block of ice in a beaker melts, there's a change in the level of water in the beaker, and then we're going to explain this observation. So let me explain to you why am I saying this question is wrong. Given that we're having a beaker like this, and there's water, and we are also having a ice like this. So this is our ice. The other portion, it is inside the water, and the other one, it is below the water surface. And initially, our beaker was like this, and the water level was like this. And then the moment we have added this ice block, is a displacement of water. So when this ice starts to melt, it is covering the same portion of the water that was displaced. So there's no new change of the volume of water. Why? Because this melting ice is just filling up the displaced volume by the ice. So there will be no change. There's a change in the level of water in the beaker, but there will be no change in the level of water in the beaker. So that is where the question was wrong. So to explain why there is no change in the level of water in the beaker, you can simply say the melting water is just filling up the displaced fluid or the displaced water by the ice block. That is our answer, and that is the explanation for this observation. So the observation is there is no change. Okay, and let us move on to the part D of our question. So the part D says a satellite of mass m orbits the Earth in a circular path with a speed v. The mass of the Earth is m, and the radius of orbit is r. So we are required to show that the total energy ET of the satellite is given by ET is equal to minus g mm over 2r. So total energy, it is equal to gravitational potential energy plus kinetic energy. So the formula for gravitational potential energy, it is m phi, and then our phi, the gravitational potential, it is minus g m over r. So if our gravitational potential energy is m phi, it is now minus g m over r. So this is the formula for the gravitational potential energy. Okay, and let us deduce the formula of kinetic energy of the satellite. So force, it is equal to what? Force, the gravitational force, it is equal to g m over r squared, and we have this equation for the centripetal force. So centripetal force, it is equal to m v squared over r. So the gravitational force, what is providing for the centripetal force of the satellite, it is the gravitational force. So we can equate these two equations to say m v squared over r, it is now equal to g m over r squared. Okay, and let us multiply both sides by r squared. So if we multiply both sides by r squared, our answer, this gives us m v squared r being equal to g m. But we want to have any relationship of v squared with g m and r. So we divide both sides by m/r. So it is now v squared being equal to g m over m/r. And this m and this m cancels. So v squared is equal to g m over r, like this. And we have this formula for kinetic energy, which says kinetic energy is equal to half mv squared. So given that mv squared, it is equal to gm over r, therefore kinetic energy, it is equal to half half m gm over r. Therefore kinetic energy, it is equal to half g m over r, or we can just say it is g m over 2r. So this is the formula of our kinetic energy. Therefore the total energy, it is minus g m for gravitational potential energy over r minus it's plus g m over 2r. So this gives us you can factor out g m over r. So we are going to be left with 1 minus is 1 plus half, like this. So our final answer will be g m over r multiplied by minus half, and if we multiply this by minus half, it will give us negative g m over 2r, like this. So this is our total energy, and we've managed to show that total energy is equal to minus g m over 2r. Okay, and let us move on to the next question, which says suggest the significance of the minus in the formula. So this minus in this formula of the total energy simply means that the total energy is always attractive. So just like the significance of negative on the equation of gravitational potential or the gravitational force, this negative, it signifies the attractive force of the gravitational force. Okay, so it simply means that it is always attractive. And we are done with our number 1. So this question paper was something like, it was very easy to some extent. It only needs you to understand some concepts, some principles, and it was a lot of general physics, like this first part of random errors, the density, the uncertainty, vectors, and scalar quantities, and there's also classical mechanics, the projectile motion. So what you need to understand under the projectile motion topic is that whenever you are answering a projectile motion topic question, just separate or divide your motion into vertical motion and horizontal motion, and then after that you're good to go.